So now we'll just get into the CMOS inverter. So when I say a CMOS inverter, a CMOS circuit, how does it look? I'll just explain. And based on that concept, let us try to build this CMOS inverter. Okay. So in general, the CMOS circuits will have two blocks. Okay. And between the first block and the second block, there is a node that connects, and we would be tapping the output from the intermediate node between the top block and the bottom block. Okay. And we call this top block as P block and the bottom block as N block. And the reason why we call them as P and N is just because the P block will have PMOS transistors, okay, whereas the N block will have only the NMOS transistors. And in general, the source terminal of PMOS will be at higher potential. But in general, when you compare the source terminal with respect to the drain, the source has to be at higher potential than compared to the drain terminal. Okay, yeah. On the other hand, when I talk about the NMOS, the source terminal of the NMOS will be at the lowest potential than compared to the drain. Okay, so these are with respect to drain terminal. Okay, this particular statements that I'm writing. Yeah. So due to which, what I do is that I would plug in the value of ground towards the NMOS block, okay, whereas the PMOS block will be attached to the VDD, okay, and in general, the inputs will go in common to both the P block as well as to the N block, okay. So whatever the input that I have, in general, feeds to both the P block as well as to the N block, and the output are in general taken out where at the intermediate node between the P block and the N block. Okay. So based on this, let us try to quickly build our CMOS inverter. Okay. So as I said, we need both P block and N block, and just for the CMOS inverter, we need only two transistors. One is a P transistor, the other one is an N transistor, and both these transistors has to satisfy this condition. Okay, so what I do is that let me try to put my PMOS transistor inside the P block. So this is supposed to be my P block. And as I said, the source potential is supposed to be at higher potential than compared to the drain. And due to this condition, I place my source terminal towards the VDD. Okay, and then the drain terminal falls below that. And right now, I have to build the N block, and we know that the tail node of the N block will be attached to a ground. Okay, and again, as I stated, the source terminal of the N block or the NMOS transistor is supposed to be at the lowest potential than compared to the drain. So due to which, I would place the source towards the lowest potential than compared to the drain. Okay, so this is the kind of notation that you would have used in your AMC. Okay, like representing arrows to represent the PMOS as well as the NMOS. But when it comes to VLSI, we generally are not comfortable with this kind of notation, but rather we are more comfortable with the other type of notation where I can represent the PMOS with a bubble, okay, and the NMOS without any bubble. Okay, so this is also valid. Clear? And you have to tie both the drains, and from the drain you would be tapping an output, which we can call it as V out. Okay, and as I said, the input supposed to go to both the P block as well as N block, and let me label the input as a voltage as V in. Okay, and this is the construction of your CMOS inverter. So now that what we do is that, yeah. So now in this case, we have just plotted the output characteristic graph. Okay, so the way that we ended up having this VTC graph is that we started with this output characteristic graph, and from the output characteristic graph, we tried to remove this variable ID, and then we were utilizing all our V in towards the x-axis, and we swapped our V out onto the y-axis. Okay, so the same similar logic we will be applying in order to get the VTC graph for the CMOS inverter. So we begin with the discussion of this output characteristic graph. The one on the right denotes the NMOS output characteristic graph, whereas the one towards the third quadrant is the kind of graph that we would get for a PMOS. Okay, so these are like individual. But now when I try to apply the value of Vn, all of these axes will get offsetted by the value of VDD. So what I really mean by that, in a minute, I will just try to talk. Okay, and even the value of VDS that has been plotted for the PMOS will be offsetted by the value of VDD. Okay, so in order to demonstrate these 2 points, let me use this particular figure. So we know that this is the value of VDS-P that I have, and the VDS-N of this particular structure. So now both these VDS has to be related to a common variable which is known as the Vout. Okay, so let us try to write the value of VDS-N in terms of the variable Vout. Okay, so this can be written as something like drain voltage minus the source voltage. We know that the source voltage was connected to the ground, so we can just write it as 0, whereas the drain node is connected to the value of Vout. Okay, so we end up having that the value of VDS-N is equal to Vout. Now let us apply the same similar logic onto our PMOS. Okay, so I don't know how you people are comfortable. Maybe if you are not comfortable with this notation, we can also use the other way, like VSD of PMOS. Okay, we can do the similar logic. Okay, so but according to the graph that I have plotted, it's basically VDS I have to take so that I end up having some sort of negative expression for the x-axis. Okay, so this axis is basically a negative expression. So which means that I have to plot as VDS. Okay, not as VSD. Okay, maybe doesn't matter in case if you're not understanding it. But what I really mean to say here is that I can split this VDSP as VDP minus VSP. Okay, and we know that this is connected to the output node Vout, so I would write it as Vout minus this VDSP, that is the source node of my PMOS is connected to the supply voltage of VDD. Okay, so now this VDSP has to be translated in terms of Vout. Okay, so what I can do is that I can rewrite this expression such that on the left side I have Vout, on towards the right side I just have to add this value of VDD to it in order to get the common expression. Okay, so our Vout in terms of VDSN and our Vout in terms of VDSP. Okay, so both of these expressions has to get satisfied by these set of equations. Clear? So having got this equation, now let us try to shift this. Okay, so I want this particular plot. Okay, now I want to shift each and every point that I have here towards the right side. Okay, so in the sense, say for example, I'm talking about a current that is at this particular origin. Okay, so I have a VDSP that is equal to 0. Now when I take that particular point, the VDSP that is equal to 0, and when I use this particular value onto this expression, I would end up having Vout that is equal to VDD. Okay, so maybe I have to take this picture. Yeah, so from here each and every point has to be shifted to our Vout axis. Okay, so Vout in terms of VDSP can be written as something like this. Okay, so now this point marks a VDS that is equal to, or VDSP that is equal to 0, right? So that is the value that when I plug in here, this point gets translated to a Vout. Okay, so this point gets translated to a value of Vout that is equal to VDD. Okay, and this point, okay, so this point would then translate towards the left side. So all of these points, right from here to here, and say for example, I have the value of VDSP that is equal to VDD. Okay, so this was our VDSP, and that value has a negative value in it. Okay, so this is minus VDD, and that value when I try to map, it will end up across the origin because of this expression. Okay, so when I take the value of VDSP that is equal to minus VDD, I would get VDD plus minus of VDD would end up having a Vout that is equal to 0. Okay, so this particular point actually ends up getting mapped from here all the way to the origin. Clear? So now each and every point in this particular Cara would then get mapped onto this. Okay, and also the currents that flows is common to both the PMOS and NMOS transistor. So whatever the current that flows here, obviously the same current has to flow here. Okay, the only thing that we have to do is that there is a reverse in the current direction. Okay, so instead of writing it as IDSP, which carries a negative current, okay, so these are the negative currents that we have to visually see them, that this has to be translated to a common current just by writing it as, okay, so the current is actually flowing from source to drain and from here drain to source. Okay, so since both the current directions has to follow the same notation, I would end up having this. So what it really means in this case is that I have to take the magnitude part and then shift each and every point towards this side. Okay, so this particular current that I'm having here would then get translated something like this. Okay, and this particular part of the current that I have here would then get translated something like this. Clear? So what we have done is that we have made a kind of mirroring image on this particular plane. Okay, where the plane is exactly at y that is equal to 0 or IDS that is equal to 0. So there is a mirroring of concept that is happening across this particular plane. Okay, so the entire axis that I have here has been shifted by an offset value of VDD. And again, we have currents in terms of negative values. Okay, so these are the currents that are happening in the third quadrant, which means that we have negative VDSP as well as negative value of IDSP. Okay, but we know that the currents that are flowing along the PMOS is from the source to the drain, because from higher potential towards the lower potential is where the current flows. Okay, so rather than writing it as something like this, we can actually write it the current flow on the other way, like from source to drain it flows. Okay, so it doesn't matter like what notation that you use. The one thing that we have to observe is that the current is flowing from source to drain, and the same current flows from drain to source for the NMOS. Okay, so both the currents has to be equal. So as I said, each and every point has been shifted here, and you are getting translated towards the first quadrant. Okay, so all of these points that I have here can be translated to our first quadrant itself just by making use of this equation. And for the current, I'm just going to use, so based on this relation, I can shift all of the negative values of currents to a positive value, okay, just by inverting this. So the relation that I have here, that is IDSP, is nothing but, just by following this simple relation, I could do this particular process of converting these negative currents into a positive current, and then I can shift all of these points. Okay, so graphically we have to do something like this, and now let us try to apply the value of Vn. Okay, so whatever we discussed is in regard with respect to the output. Okay, Vout. Okay, in the same similar way, we also have to work with respect to the value of Vn. Okay, now as you could guess that the value of VGS of the NMOS is exactly equal to our Vn itself. Okay, but when it comes to the VGS of a PMOS, this needs some sort of insight into this particular expression. Okay, so let me just try to bring this particular picture. Okay, now let me write this VGS of the PMOS as VG, again with respect to PMOS, and the source with respect to the PMOS. Okay, now if I see the gate input is basically connected to the Vn, right? So I just replace this Vg of the PMOS with Vn. But the source node of our PMOS is connected to the VDD supply. Okay, so again, this is something that we had the same issue with respect to the VDSP of the PMOS, right? So in the same similar way, we have some sort of relation, something like this. But as I said earlier, we want a plot between Vout and Vn, okay, not in terms of VGSP or something else. Okay, so we need some modification for this expression such that we end up having an expression in terms of Vin rather than in terms of VGSP. So I just do the simple math of shifting the variables from one end to the other end, and I would end up having something like, so this is just a simple transformation that I did. Now, having got this simple transformation, now that we have to apply this set of input condition and see which transistors are on and which transistors are off and what current flow across them. Okay. Now let us begin with the simple case where we will shift the value of Vn right from the value of 0 all the way towards VDD. Okay. So let us begin with the first case where I have a range of input from 0 volt to all the way to the threshold voltage of the NMOS device. Now, under this condition, let us try to evaluate the value of VGS of NMOS device as well as the VGS of the PMOS device. Okay, so this gives us some sort of insight. So I'm just trying to rewrite them. And also in terms of Vout, we will express later. Okay, yeah. So now what happens to this NMOS device when I apply a VGSN? We know that the VGSN is nothing but it's equal to V in itself. Okay, and we know under this condition, under the given input condition, we know that the NMOS device would be off. Okay, maybe I have to label them as something like N1 and P1. Okay, so that my transistor N1 is turned off. But what about this PMOS? So again, I just write this. Let us take a simple value of 0 for the value of Vn. And we have already know that this has to be offsetted with some sort of supply. Okay. So this expression is nothing but Vin minus VDD is what I've rewritten. Okay. And based on the simple value of 0, when I plug in here, I end up having a large negative value across this PMOS. Now, is this transistor on or off? This might seems a bit of complication just because you end up having some sort of negative quantities. And you have to understand that for a PMOS, everything is of negative. Okay, say I generally go with some sort of hand notation or hand signal for knowing whether the transistor is on, or if at all if the transistor is on, which region of operation. So all of these identifications can be shown with some sort of hand signal. But let me try to explain this. I just compare the region of operation of a PMOS with respect to an NMOS first. Okay, so let me just talk about this, and later I will spend some time on this particular PMOS device. Okay, if at all, if the NMOS is off, we know that the value of VGS is basically less than VT or less than or equal to VT. Okay, so this is the condition that I have, and irrespective of whatever the value of VDS that I have, it still doesn't conduct any current. Okay, so it doesn't matter whatever the value that I have here. Okay, whereas if I have a value of VGS that is greater than the value of VT, then there are two conditions that we know, right? So one is the linear, the other one is the saturation. The way that I'm going to identify whether I'm in linear or in saturation depends on the value of VDS. Okay, so here we have to rely on the value of VDS here. So this VDS, if at all, if this is less than VGS minus VT, we say that the transistor is in the linear region. Okay, and if my VDS is greater than or equal to VGS minus VT, we say that our transistor is in the saturation region. Okay, so in this case, the one thing that we can think is that whether the value of VDS is more positive than the VOV or less positive than the VOV. So in that way, if I think, we could see that if at all, if my VDS is more positive than compared to the VOV value, then I can say that my transistor is in the saturation region. Okay, so the same phenomena we'll just try to apply with respect to the PMOS. Okay, so as a first condition, so what type of relation I need to fix here? Because as I know that my threshold voltage of a PMOS device is going to be a negative value. Okay, so this is a negative quantity. Now, how will I compare these negative values in order to ensure that my transistor is off? Okay, so I want an off condition. And how will I write this in terms of logical expression?
VGS greater than VT, I guess.
Yeah, you see, there is something, a -1 is more compared to -2. Okay, so this is exactly opposite to the case when I have a positive value. Okay, so in this case, since we are comparing a negative value, the negative values of small values, it's higher than compared to the most negative value. Okay, so if at all, if I want to turn off the device, I want this VT to be more negative than compared to the negative value of VGS. So now, why did I say that this is supposed to be a negative value? Because as I said, for a PMOS device, the source will always be at a higher potential. Okay, so in other words, what I can say is that let us compare with this particular PMOS. Okay, so with respect to the inverter PMOS, our source is connected to the VDD, and the gate can also get connected to VDD. That is a different story. But there is a range of voltage that the gate can accept. Okay, so it can go from 0 all the way to VDD. So under normal situation, what happens is that the value of this VGS can undergo in terms of negative. So VG minus VS, where this minus VS is always fixed to VDD. But there is a range of voltage. So say, for example, if I am fixing a value of 0, then I would end up having a value of VGS in terms of negative. If I fix the value of VG to the most positive supply, then I end up having some sort of 0. So the values that this VGS of a PMOS device that accepts falls from minus VDD all the way to 0. Okay, it cannot go as a kind of positive value. Okay, this is the range of voltage that the VGS of a PMOS device can accept. Okay, so in general, it's a negative value that it can accept. Clear? So now, is this negative value is more negative than this VT? That is how we have to think. Okay, so more negative in the sense, let us assume the threshold voltage of our PMOS is minus 0.5. Okay, now when I say I am 0.3, is this transistor is on or off? Okay, when my VGS is said to be equal to 0.3 volt, is the transistor is on or off? So in this case, I have to compare whether I'm more negative than the threshold voltage. Okay, so in this case, I'm less negative than compared to the threshold voltage. Hope that it makes sense. Okay, so in a way, I have a situation where this minus 0.3 is having, is having this condition where minus 0.3 is more than compared to minus 0.5 value. Okay, so in a way, this transistor is off. Okay, so even this one has to be returned something like this. Okay, if you have any doubt in this regard, please let me know. That is, I'm just comparing in terms of negatives. Clear? So due to which the sign would get inverted here. Yeah. So now hope that you're clear with this first expression, whether the transistor is on or off. Just by comparing who is more negative, I can say whether the transistor is on or off. Okay. If the value of VGS is less negative than the negative value of VT, then the transistor is off. If the value of VGS is more negative than compared to the value of VT, then the transistor is on. Okay, that's it. So now let us go for the other condition where my VGS is more negative, which means that I have this situation. Clear? Now under this situation, the transistor is on, and right now I have to see whether I am in linear region or in the saturation region. So the way that I can distinguish both these regions is by looking at the value of VDS. Now here, as far as the NMOS is concerned, I said that the value of VDS, when it is less positive than compared to the value of VOV, okay, we said we are in the linear region, right? So we would adopt the same kind of notation. If at all, if my value of VDS is less negative, okay, if it is less negative than compared to the VOV value. So VOV is nothing but VGS minus VT. Clear? So whenever I deal with VOV for a PMOS, the VOV has to be a negative quantity. A VOV for an NMOS device will always be a positive quantity. Clear? So we know that this value of VOV is always a negative value. The only thing is that I'm just comparing whether the value of VDS, which is again a negative value, whether this negative value is more or less compared to the negative value of VOV. That's it. Okay. If at all, if the value of VDS is less negative than the VOV, which is already a negative value, then we say that the transistor is in the linear region. However, we said over here. So in this case, I said that the VDS value of an NMOS device, if it is less positive than compared to the VOV value, then we said that the transistor is in the linear region. Okay, so here again, I would say the same argument. In this case, the VDS of the PMOS has to be less negative than compared to the negative value of VOV. So how will I say that it is less negative? By using this symbol. Okay, and whenever my VDS is more negative, okay, if it is more negative than compared to the value of VGS minus VT, which is again a negative value, then I would say that I'm in the saturation region. So when I say that I am more negative, which means that I have some value which is maybe minus 1.5. Okay, so this minus 1.5 is more negative than this minus 1 value. Okay, so due to which my sign would then change here, because this has a greater value than compared to this minus 1.5 value. Clear? And due to the same reasoning, I end up having this. The only thing that I follow here is that whether I'm more positive or less positive in order to distinguish two regions of operation. Okay. Whereas when it comes to the PMOS, I'm comparing whether I'm more negative or less negative than compared to the VOV of my PMOS. Okay. So if you could able to fix your mind to this concept, it becomes pretty clear. Okay. Whether I'm more negative or less negative. That's it. Okay. I hope that I have not confused your basics. Because this is my way of thinking. So in case if you have your own way of thinking, it's fine. Yeah. Now the answer for this question, which I asked, can be derived right away from here. Now, clearly the VDS of the PMOS device is equal to minus VDD. So this means it's more negative. Okay. Let us assume that our VDD is equal to 1 volt or something, because I have the graphs where I have marked it as 1, okay, as the maximum value. So let us assume that we have this VDD as 1, and the threshold voltage of the device can be like, it's a weird number, but still, let us go with this number or something, okay? So let us assume that we have this 0.1 as our threshold voltage of the PMOS device, okay? So with this, let us try to think. Now, when I say I have minus 1, and that I'm comparing with minus 0.1, whether the transistor is on or off, the VGS is more negative than compared to the threshold voltage of the device. Okay, so this means our PMOS is on. Okay, so the answer of A is right, and the reason could be thought of with this simple process, whether I'm more negative or less negative. That's it. Okay, however, we had a thought process for this NMOS. If we apply in terms of negatives, it becomes pretty easy. Clear? Yeah. Now, identifying whether the transistor is on or off is fine. But once you know that the transistor is on, now our task is to identify which region does this transistor operates in, right? Yeah. So how would we get that information? Can there be any thought process for this? Because there is something, this transistor is off. Okay. I don't have this particular transistor in my path just because it is turned off. We know that this particular transistor, which is the PMOS transistor, is on. Okay, this guy is on, and what's supposed to be the value of the Vout? It should hold such that even though the transistor is on, it doesn't conduct any current, because the bottom transistor is not consuming any current here. Okay, so in the sense, I have this IDS N that is equal to 0, which means that even my PMOS device should adopt the same current flow. Okay. So due to which, even this transistor, even though it is on, it should not conduct any current. So which region it has to operate such that it performs this kind of analogy?
Cutoff.
On means cutoff will not come, right?
Sorry.
Yeah. Okay, so let me just give a simple clue here. Okay, you have a resistor of 1K, okay, and you have 2 volt here and a 1 volt here. Okay, so what would be the current through the resistor?
1 milli.
1 milli. Okay, now what happens if I make this one as 2? What happens to the current? It becomes 0. Okay, so now what's supposed to be the value of this guy, V out, such that there is no conduction of current here?
VDD.
VDD.
Yeah, it's supposed to be VDD. You see, when maybe I will use this graph that I have here. Maybe can I work out with respect to the NMOS? Yeah. So we know that with respect to NMOS, I discussed the same thing because the graph of my PMOS is inverted. It becomes hard for us to really visualize that. So let us assume that I have this kind of curve. And we know that the value of VGS that I have is more positive, okay? But still, it doesn't conduct any current. So means, in this case, you could see that there is some amount of current that is flowing through the device, okay? And the corresponding value of VDS is defined by this particular x-axis. And if at all, if I'm choosing this as my current, the corresponding VDS value is defined something like this, okay? Now, in this case, you could see that there is a drastic drop in the value of current the moment the VDS is becoming 0, okay? And as I move down this particular line all the way, when I'm having at this particular point, okay, the transistor is on, but it doesn't conduct any current. So this means that I'm in the deep linear region, okay? I'm on this axis. I'm still on this axis, okay? On this axis, but it should not conduct any current, means that the VDS supposed to be at 0. Okay, hope that it makes sense. If you want, I can replot the same graph with respect to the PMOS. So this is the carrier that I have for a supply of minus VDD across my VGS of the PMOS device. This particular axis that I have is basically VDS of the PMOS device. And we know that this VDSP always takes a range of value, and that range of value falls from minus VDD to a 0. Okay, so this axis doesn't matter for us. The axis that matters is this negative scale of this x-axis. Clear? So now when I pick this as my VDS, which is more negative, okay, we could see that there is some current flowing through the device. Okay, now as I move down this VDS line, I reach the point where the VDS becomes, or the VDSP becomes equal to 0. At that particular point, we could see that the current is actually becoming 0. Okay, so now in order to make this VDSP that is equal to 0, I have to ensure, okay, let me apply this condition here, that my VDS of the PMOS device is supposed to be equal to 0. So in order to make it 0, let me write the expression for this. So VD minus VS, okay, that's supposed to be equal to 0. Now we know that the source potential is already connected to the supply VDD. Now, in order to have a 0, I have to add a VDD to the drain of my PMOS, okay, in order to ensure that it becomes 0, right? So in this situation, I would have my Vout, which is nothing but the drain potential of my PMOS device, that is connected to VDD. So only when I have this situation, even though the transistor of PMOS is on, in order to make now to conduct, I have to move this transistor to deep linear region or deep triode region. Okay, so that is the logic behind this. I hope that you have understood this phenomena. Okay, even though we have huge value of VGS, but it doesn't have enough VDS in order to conduct the current. Okay, so we have whatever the potential on one end, the same potential has to appear in order to make the current to stop to flow. Okay, so the same logic that I've said for the resistor, because the channel is on and I can visualize this transistor that is on as a kind of resistor. Okay, now whenever I have the transistor that is off, I can still visualize that path as a resistor, but the path is a kind of open circuit. Okay, so there is no connection. It's a very high impedance between the source and the drain. That is how I can visualize this particular path. No current can flow, and it can be thought of as a kind of open circuit. Okay, the moment the transistor is on, we can visualize something like a kind of resistance. I'll talk about this resistance after a while. Clear? Yeah. So now this is the condition that I have till the value of Vin falls between the range of 0 to Vt. Okay. Yeah. So now let me just show the graph that I would get. So in this case, when the value of Vn that is equal to 0, we know that the NMOS transistor would be off. Okay, so off in the sense it doesn't conduct any current, and that has been shown through this graphic. Okay, with this magenta color. Okay, it doesn't conduct any current, and that graph actually intersects with my PMOS graph, which is capable of conducting the current. Okay, And we know that this Vout is nothing but our VDS of the NMOS device. Okay, so that is equal to our VDD. Okay, or Vout can be rewritten in terms of VDSP, something which we have discussed. Clear? So even based on that, we end up having this as our intersection point. Okay, this is the intersection point right now that we have for the Vout. I hope that this particular graphic is clear. And now what we do is that we will try to increment the input voltage at every step and then see what happens after this. Clear? So this is an input voltage where I have just increased the input voltage beyond the value of VTN. Clear? As I said, according to the graphic that I've drawn, the VTN or the VTP both were taken to be around 0.1 or 0.15. It's fine. Okay, so any of these values would hold good for us. So since because I'm more positive than compared to the threshold voltage of the NMOS device, obviously under this condition, having this as 0.2 will actually turn on our NMOS device. Okay. Now, which region does this transistor moves in? One small hint that I can give is that you can think of our discussion that we did in the last class. Okay. And also let me write the condition for the PMOS as well. Now we have to see whether the PMOS is on or off, right? So obviously the PMOS is on. The reason why I'm saying is that we have to compare the VGS of the PMOS device, and it can be written as VG minus VS. And the source is always connected to the supply, and the value that I have fed to the gate is obviously 0.2, right? So which is a value which is slightly greater than the threshold voltage of the device. Okay. Okay. Let us assume the VDD is equal to 1 volt, and I have 0.2 volt across the gate. So we end up having something like this, which is more negative than compared to the threshold voltage of the PMOS device. Okay. So in this case, I'm going to assume that the PMOS has a threshold voltage of minus 0.1 volt. Okay. I'm more negative than this guy, which means that I'm on. Okay. So this guy is on, but what is the region of operation? So again, I have to reset the poll, but let me just come to the conclusion here. Okay, the trans is on. We still yet to identify the region of operation, but that can be identified only after identifying what region this NMOS is operated in. Okay, now the final conclusion or the takeaway message in the last class was that we know that the NMOS device actually moves to different regions through a particular path. What is the path? If at all, if the NMOS is off, it takes the path from off condition to saturation first, and then only it moves to linear region. It cannot switch from off to linear region. It cannot happen at all. Okay, and that was the discussion that we spent for 1 hour. Clear? So in a way, just before this value of Vn, we had the transit of our NMOS being turned off, right? So under this condition, our NMOS was off. So from the off condition, obviously I have to end up into the saturation regime. Okay, so in this case, the answer B is right. So now the trans is on and it is in the saturation condition. Now, does this conduct more current or less current for the given value of Vin? Okay, so I'll try to fix the transistor here. Okay, now I have a very small value of VGS across this device, and due to which the trans is on, and the current flow, do you think it will be high or less? So we know the current is basically proportional to something like VGS minus VT, okay? And then the whole square is there. If the value of VGS minus VT is a very small positive value, then will this current will shoot up or it will be less?
Less.
It would be less, right? Yeah, so we have a very less current, but this guy has a lot of VGS, okay? Say for example, let me use the graph that I have plotted here. Just because our transistor NMOS is just on and it conducts only 0.1 milliampere of current, okay? But according to the given condition, the PMOS is capable of conducting more current actually. So for the given value of minus 0.8 volt, the magnitude of current it can conduct is basically given as for the corresponding value of VDS, it can conduct a maximum current of 1 milliampere. But still, we don't want that current to flow, right? Because the bottom transistor is not accepting this 1 milliampere of current. It can accept only 0.1 milliampere of current. So how I can do this? With the PMOS that is capable of conducting a very large current of 1 milliampere, still, I don't want that 1 milliampere of current to flow through the device. So basically, the PMOS has to operate in which region? To
Linear
make this,
region.
huh?
Linear region.
Yeah, it's supposed to be linear, right? So in a way, if at all, right now, I need some current to flow. And I can think again as a resistor. Okay, so think as a resistor, and you want a very less current, which means that I need to drop the other end of my potential to be like 1.8 volt, so that this 1 kilo ohm of resistance can conduct only a very small tiny amount of current through the device. Okay, if I shift this guy all the way to a very low potential, like a 0 volt, then what happens is that it conducts a very large current. Okay, we don't want such a large current to flow, which means that the other end of my terminal is supposed to be a value that is closer to the supply voltage, such that even though the transistor is capable of producing a very large current, we want to restrict the current through the device. So due to which we want to hold this value on the other side of the resistor to be a value that is closer to supply. Clear? So in a way, I can reduce this current. So we want just 0.1 milliampere of current, okay, which means that the corresponding VDS I need to have supposed to be small. Okay, the difference between the source and the drain terminal is supposed to be very minimum. Clear? So in a way, my VDS of the PMOS device is no more equal to 0, but rather a small negative value. Okay, this value is supposed to be small. So due to which my Vout, since because our VDSP is a negative value, the value of Vout is almost closer to the value of VDD. Okay, approximately closer to the value of VDD, but still it's a value which is slightly lower than the value of VDD. Clear? And now the discussion has to move on. So let me just try to switch to the other value where I have 0.4. And when I have this 0.4, the VGSP of the transistor will be minus 0.6, whereas VGS of the NMOS transistor is 0.4. Clear? So they both actually intersects at this particular node, and just because our NMOS device is capable of accepting only this amount of current, okay, you could see that the transistor of NMOS is intersecting in the region of saturation, but the transistor of PMOS is intersecting in the region of linear region. Okay, so even in the previous case, you could see our transistor NMOS was in the saturation region, but our transistor PMOS was in the linear region. Okay, even for this input, we have the same similar condition. Now let us go for an input that is equal to 0.5. Now under this condition, you could see that both these points are intersecting somewhere in the midway, okay, where both the transistors are in saturation region. Okay, as I move the value of this Vin greater than the value of 0.5, then what happens is that our transistor PMOS will stay in the saturation region. Okay, but what happens is that our NMOS transistor was getting into the linear region. Okay, so you could see we started from cutoff, and from cutoff, our NMOS device has entered into saturation. Okay, it was in saturation. Now it has gone into linear. Okay, the travel is always from off to saturation and then only to linear. And as I move further, when the value of VGS is equal to VDD, okay, so I'll just write the final condition. Okay, so I have this VGSP, and my Vn is basically equals to VDD. Now, what's supposed to be the value across this VGSP? So again, I can write it as VG minus VS, and we know that the source node is always connected to the VDD. We have VDD here, and the gate is connected to our Vin, and due to which when I apply this condition, we end up having a VGSP that is equal to 0. Okay, so this 0 means that the transistor will be off, turned off, right? So due to which our PMOS device would be off, but our NMOS device would be on, because the VGS of the NMOS is right now equal to VDD. Okay, because of this input voltage, I have this VGSN that is equal to VDD. Now the NMOS is on, we know that, but the PMOS is not able to conduct any current. So due to which even the NMOS should not conduct any current even though it is on. So what's supposed to be the value of its VDSN such that it doesn't conduct any current?
0.
Yeah, it's supposed to be, because we know that the source node of our transistor NMOS is connected to the ground. Okay, so whatever the voltage that I have here has to be applied here such that there is no potential difference between the source and the drain, and due to which the current becomes equal to 0 even though the transistor is on. Okay, so I think I've taken more time. So this is the condition that we have. Now, before I leave this particular topic, I just want to make a quick review. Let us go from beginning, from a value of 0. Okay, so in this case, we found, we will talk with respect to the PMOS, the blue curve. Okay, you could see that when my input is at 0, the PMOS was in deep linear region. Okay, it was in linear region, and for the next input, it was still in the linear region. I'm talking about the blue curve. Okay, and we were in linear region again, and we went into saturation. And after saturation, we were entering into saturation again, and then we got into cutoff. Okay, so as far as the PMOS is concerned, the travel was in the reverse direction. We began with linear region, and then we moved on into saturation region, and from saturation, we ended up into the cutoff region. Whereas our NMOS device started off with, this is with PMOS, this is with NMOS. Okay, we started with off transistor, and then we moved on into saturation, and then we moved into linear region. Okay, so the travel is always something like this. Okay, you cannot shuffle the path. The path is always in this particular direction. Okay, so if you could able to understand this, yeah.
Sir, in the step where both are saturation, will the output be floating?
The output will not float. Yeah, the output will never float actually. So because for the corresponding value of VGS, we need to have some sort of potential drop. Because in order to conduct current, because both the transistors are on, this is something, yeah, it cannot float. Both the transistors are on, and it has to conduct some part of the current. So there's supposed to be some potential difference between the supply, VDD, and this node, which is Vout, such that it conducts a current. So it cannot float actually. You have to have a definite voltage in order to have this phenomena to happen, in order to make the current to flow. So you can either talk with respect to the PMOS or with respect to the NMOS. Both has to get satisfied in order to solve this particular issue. So most of the time, in that case, it would be at this condition, such that the resistance of the PMOS channel and the resistance of the NMOS channel, okay, both supposed to be equal in order to have this condition. We'll talk about this. We'll talk about this condition, but this is the obvious condition that we wanted. Okay. Since both the transistors that are on, I can visualize the on transistors with resistance. Okay. And if the resistance of both the transistors are same, then our Vout would be equal to, what would be this Vout? For Vin, that is equal to, yeah, it would be VDD by 2.
VDD by 2.
Okay. Yeah. So that happens only when I have equal resistances.
So in the last couple of classes, we have been looking at the CMOS inverter. Yeah. So having got this particular structure, we found a relation. Basically, the graph that we were getting is some sort of graph. Okay. So this particular graph is a combination of all different input conditions. Okay. So each of these dots that has been plotted corresponds to a particular value of input condition, the amount of current that flows through the circuit. Okay. So now in this, we can get rid of this current component. Okay. And what we can do is that we can just shift this particular Vout axis to, from the x-axis towards the y-axis, we can shift it, and towards the x-axis we can put our Vin. Okay. So again, these are for different values of Vin is what is being plotted here. Okay. So in a way, when we try to eliminate this ideas out of this equation, we end up having with some set of neat graph. Okay, so I'll just draw the graph of it, where I have this V in and V out as my y-axis. Clear? So we know that when the value of input is at 0, or within the range between 0 to VTN, when the input value, we know this bottom transistor, which is N1, was completely off. Okay, but the PMOS was on. And because the NMOS is off, we said that the current component conducted by the NMOS current would be equal to 0, and the same has to be satisfied by the PMOS. Okay, so even though this PMOS was on, but it should not conduct any current, means that the potential difference between the source and the drain is supposed to be same. Okay, only when we have VDS that is equal to 0, one could achieve a current value of 0 here. Okay, so in those conditions, because the source is connected towards the VDD, I want the drain to have the same potential such that the VDS of our PMOS device becomes equal to 0. Okay, which means that our Vout is supposed to be equal to VDD when I'm at between the input conditions of 0 to VTN. Okay, and we can also see the other extreme case when I'm trying to have an input voltage within the range of VDD minus of VTP. Okay, so I'm just putting a modulus just because we know that the threshold voltage of the PMOS is a negative quantity. So I'm just taking the modulus of it and then I'm trying to write it here. Okay, and the other extreme value that I can have here is my VDD. Okay, so within this range, what happens is that our PMOS transistor would be turned off because it doesn't have enough VGS. So due to which the transistor would be off. Now, in this case, the current that flows through this PMOS would then be equal to 0, but the NMOS transistor is on, but it cannot conduct any current, means that the VDS of our NMOS transistor is supposed to be equal to 0. Now, we know that the source is already connected to the ground, and in order to make this VDS to be equal to 0, I also have to pull this drain of my NMOS towards the ground. Okay, and that is how I can make this VDS of same potential such that I end up having a VDS value that is equal to 0. Okay, so due to which we would have, maybe I will use a different color. So the value that I would get for this range of input would be equal to 0. Okay, so this is the case where my PMOS is off, okay, but the NMOS is on. Even though the NMOS is on, it is in the deep linear region. Okay, so on the other hand, where we have this guy, here in this case, our PMOS was on, but it was in the deep linear region. Okay, but the NMOS was turned off. Okay, and now let us move from this case. Okay, so I just try to increase the value of Vn more than the value of Vtn, and due to which what happens is that the NMOS transistor slightly turns on, and due to which the current conduction that happens through this NMOS would be very minimum. Okay, but the value of VGS that is defined for the PMOS is very large, but still, in order to satisfy the same current flow through both the transistors, the PMOS would be still in the linear region, but with some appropriate VDS value. Okay, the VDS value will no more be equal to 0. Okay, so we will have a non-zero value, but that non-zero value was a bit small. Okay, or the value of this VDSP would be small. Okay, so now already we know that the source is at higher potential, means which is at VDD, and obviously the potential at this particular drain is supposed to be less than the value of VDD. Okay, and due to this reasoning, the Vout, which is connected to the drain of our PMOS, has to drop down. Okay, such that it creates a potential difference between the drain and the source, which is at VDD. Okay, so I'm just trying to create a potential difference by moving this Vout towards the lower side. Okay, now there is a particular zone, maybe it slowly varies. Okay, and there is a particular zone where there is a quick variation, and then it moves into something like this. Okay, yeah, so now I can just divide this as one more region, where here in this case I'm going to assume that the beta P is equal to beta N. Okay, so this is a kind of a region that separates, and in this particular zone I will have both the transistors in the saturation region. okay? And this region we call it as C. I'll talk about different regions, okay? And there is a particular zone for the value of input falls between 0 to VTN. We call them as region A, okay? And in case if my beta N is equal to beta P, then the region C will fall exactly at VDD by 2. Clear? It is a very thin line. There is no width for this particular region C. It's just a single line that occupies this particular region C, okay? And obviously, we have one more region where I fall between this VDD minus VTP to VDD. We call this region as E, okay? Now, obviously, we are left over with two other zones, which is this zone and this zone, okay? So we will name them as B and D here, okay? So we can basically split this into 5 different regions of operation here. Now let us look for the region of operation across B as well as across D, okay? Now in this case, my NMOS has moved from off to what region? Because as I said, either it is an NMOS, either it is a PMOS, doesn't matter. From the off, it just moves into saturation. Okay, and from saturation it can move to the linear region, right? So the flow can reverse as well, okay? But the point is that you cannot jump from off to linear, okay? That particular path doesn't exist, okay? The path only exists which can flow something like this. So since because only this particular path is always valid, from the off, the NMOS, when it gets turned on, it moves into saturation region. But the PMOS would be still in the linear region because it has to conduct a very less current. Even though it is capable of conducting a very large current, it has to conduct very less current, due to which the VDS of our PMOS would be less negative than negative value of VOV of the PMOS transistor, okay? So due to which it would be in the linear region, okay? In region D, we will move from the reverse direction. So we were in region E, where the PMOS was off, and the moment I cross this E region, when I'm entering into the D region, obviously it is this PMOS has to shift from off to what is known as saturation. And our NMOS, which was on and it was in the deep linear region, stay in the linear region itself, okay? Hope that it makes sense. Yeah.
So
Yes.
both when they are in saturation, is it only at a particular point, or
Yes,
is
it's only at a particular input condition. We will have both the transistors to be turned on, and they both will be at saturation. It is only a single zone or a single point.
okay?
Okay.
Depending on the transistors, could it be a band, like a region C?
No. It is not. That is what I said. Like only for a single input, we have this region C. Whereas when you take region A or B, there is a wide range of input where this A, B, D, and E will fall. But whereas the region C will fall only at this particular zone. Okay, under the assumption that the value of beta N is equal to beta P. Otherwise, we'll have different this value where the C sits, okay, for the input condition that we have here may shift towards the left or towards the right. We'll talk about it in the coming session. But as far as the C point is concerned, C is just a single point or a single input condition. There is no range of input, okay? So let me put that in a kind of table so that you will better understand this, okay?
Excuse me, sir, I had a doubt. Sir, in the C region, you said it's only a particular point, right? So what will be the output values? Won't it be in a range of values?
The output would be it is a sharp decline actually. So you can actually fix it to VDD by 2. For the condition that I have written down, we can fix that value to be as a single point, okay? So it would be something like this. There is a very sharp decline. There is as you said, there is a range of value, but one can choose as a mid value here, and that mid value can be taken as VDD by 2, okay? But you are right. To be frank, there is a range of output for a single input, but nominally the transfer will take a single value, or the general CMOS inverter will take only a single output. It cannot have all the output values at that particular node. It will take a single value. and that value would be equal to VDD by 2 for the input, which is VDD by 2. And this is the condition that we will have for beta n that is equal to beta p. Okay, so since the output cannot take a range of values, it would settle down to an equilibrium condition, and that equilibrium condition would define the output to be at VDD by 2. That's it. Okay, but there is a sharp decline at that particular zone. So in this case, when you try to write this as a kind of table, you could see that there is a range of inputs for A, B, D, as well as E. But when we have C, it is only a single input that we have, where both the transistors are in saturation zone, and the output in general can be returned as a sharp fall. Okay, so there is a very sharp fall, and we cannot really predict the value of it. Okay, so but one can assume that this value has to stay to an equilibrium condition, and that equilibrium condition can be returned as something like VDD by 2.